Hello, everyone. I am here to talk about the SLA 750 and the SLA 750 dual printer. We introduced this machine a couple years ago. This is our flagship production system. This is a great slide to kind of give you a quick overview, and then we'll dive a little bit deeper into some of these advancements and advantages of this platform. To begin with, for those of you guys that already run SLA, our large frame machines have traditionally been around a watt of power at the vat. This machine bumped that power up quite a bit. We have 3 watts of power at the vat, using up to 2 4-watt lasers. This gives you much faster draw speeds, and with the ability to have a dual configuration, a dual laser configuration, you can pick up even more drawing speed with this format. We use new hyperscan vector technology. It's just a fancy way of saying we have new scanning algorithms that allow us to draw our vectors more efficiently, and so it becomes really the best in class for vector-based scanning laser system. For those of you guys not familiar with SLA, SLA is the original 3D printing technology. It was actually invented in 1983. We shipped our first machines in 1987. It's called the SLA-1. And so this is building on that great technology. It really is still the technology to beat when it comes to building accurate parts in 3D printing. It's really the only non-contact layer additive technology out there. So at no point do we have a roller or a blade or a sweeper or a squeegee or anything making contact with our part as we print. And so that allows us to build very accurate in a semi-buoyant environment. So minimal supports. It really is the technology to beat when it comes to building accurate parts. So based on that, we returned to our roots in some ways with this machine. Simpler frame design, went away from cantilevered recoder, where we actually are running 4 motors to level 2 rails. So our recoder is actually attached at both ends. We still have a removable vat system. This machine is set up to be able to go automated workflow with a robot being able to start and stop prints. We went back to gravity feed for our material. So again, for those of you guys that run SLA, if you've run a large frame SLA machine or even our small frame machines in the last 19 years or so, we utilized peristaltic pumps for moving material. We've gone to gravity feed and then a displacer to displace resin as we print. Resin much quicker. It's a better system, less wear with tubing going through a peristaltic pump. Very nice interface, ability to do remote monitoring, and a machine that's really built to last. So as we go to the next slide, generation large frame machine. It is upgradable to a dual. That dual is going to give you even more speed improvements, up to 3 times throughput on our draw speed, so that drawing time. So when you look at build time with these machines, it's your actual curing time, your drawing time with that UV laser or your 2 UV lasers, and then the layer additive process. So where you're going to see that throughput is that extra speed on draw time because you're utilizing a dual laser system. The dual laser, if you go to the next slide, the dual laser system is unlike what we've done in the past with dual lasers. These 2 lasers can reach everywhere on the platform. So that allows us to not have a seam in our part. So whether you're drawing dozens or hundreds of small parts, or you're drawing 1 large part, you're not going to see a seam anywhere. So we calculate the vectors for each layer, and then those 2 lasers are able to share the duties of drawing those parts. And then 1 laser will be dedicated to drawing the outside vectors of the part so that you don't see a seam where the 2 lasers were stitched in the middle. So that gives us a huge advantage again to building a very nice quality part without having the issue of a seam in the part. The other advantage you have with the dual laser is the ability, if needed, if for some reason one laser needs calibrated or some sort of maintenance done to it, you do have the option to draw just with the one laser, and you're able to still draw anywhere on that build platform. Next slide, please. This is showing you the difference you get in larger throughput. So the machine that this one replaced was the Pro X800. That Pro X800 had a build area of 750 by 650 by 550. This machine squares out that build area to 750 by 750 by 550 with also the option to have a short or shallow vat for those of you that are building aligners or shorter parts and don't have the need for that full vat. So that does give you a 15% larger build area than that Pro X800 machine, 100 millimeters wider in that X direction of your build area. And what's interesting is this machine, footprint-wise, ends up being very similar to the machine that replaced. So we became more efficient. We went from a dual frame system to a single frame, one beefy frame on wheels, easier to move into place at installation, and yeah, again, utilizing the space better than what we did with previous generations. The next slide here, you'll see that we have a self-calibrating recoating system. We've had this in the past on previous generation large frame machines, but we utilized a cantilever recoater design that was much beefier, much larger. It required us to move further in that Y direction when we were sweeping, just to get out of the way so that we weren't printing in the shadow of the blade. You'll see here that the blade is much more streamlined. It's much smaller. It actually utilizes a channel type system where I can drop the blade in and out very easily. There's nothing to unbolt, nothing to even loosen to be able to pull that recoating blade out, clean it, maintain it, and then place it right back in and get it to go right back to where it was. You'll also notice in the image to the right, those 4 blocks you see there, those are leveling motors. So we're able to calibrate much quicker than we were able to on the previous generation machine as well. So it does allow for the machine to calibrate within 15 minutes or so. And we even have a quick calibration method as well if you just want to double check that that blade is still calibrated to the resin surface. Being a resin-based system, that whole machine gets leveled to that resin level. And so it's critical in order to build accurate parts that we know where that blade is in relation to the resin. So there's leveling sensors at both ends of that recoating system that basically bounce a laser to the resin surface back up to a sensor, and we're able to measure very accurately within 20 to 30 microns where that resin surface is. And so that allows us to build very accurate layers as we basically build 2.5D cross sections of a 3-dimensional part. Again, for those of you guys that are not familiar with SLA, recoating is a critical part of building in a UV-based, resin-based system. And so to have a blade that we can calibrate very quickly and be ensured that it's very accurate, easy to clean, easy to maintain, it is critical. Next up, you'll see that we have an automatic material feed system. We utilize gravity in order to do so. Instead of having peristaltic pumps mounted to the front of the vat, we've gone to a much simpler vat design. Again, that tubing was a wear point for my production customers that are running these machines 24/7. That was something that had to be replaced on a regular basis. So going to gravity feed, less moving parts, much simpler to add resin when needed. The vat is still removable. So if you go to the next slide, you'll see the vat is actually removable. If you're familiar with large frame vats, they can be very complicated on the front. We've kind of returned into a much simpler design. Really, the vat is heated, stainless steel, not a lot of surfaces to drip resin on, which, again, for those of you guys that are familiar with this process, being able to keep a clean machine is important. Yeah, anything that touches the resin can stay with that resin. So the elevator, the platform, the recoating blade, all that can be removed with that material, and it allows you to push in a new vat with an elevator with a new blade or recoating blade, and switch to a different resin very quickly with this machine. The machine has been entirely redesigned from the ground up, and one of the things that was on my wish list with the introduction to the machine was covering up a lot of the open gaps that you see in the build chamber. So you'll see a lot of stainless steel brush surfaces, and really that is, again, to be able to keep that surface clean and be able to control drips and when pulling parts in and out of the machine. So if you look at our previous generation machines, there's much more of an open architecture, a lot of gaps and spaces between the vat and the frame. And now we're back to rim covers, which, again, it's returning a little bit to our roots, but much cleaner design. Very high-end components. 3D Systems is very much known for building machines that last. We were never good at planned obsolescence. You know, it's not unusual to see machines that are out there that are 20 plus years old still building great parts. And so this machine is going to be no different. It's very much designed for production, lights out, around the clock type operation with minimal interaction, minimal customer serviceable parts. You know, there's not a lot of tuning that you have to do on a daily or weekly or even monthly basis. Really keep the machine clean, and it will be good to you and build you a lot of very active parts for years to come. The user interface is all brand new as well for this machine. We used to use an Android type interface that communicated with the controller. We are now back to this. This is a monitor connected directly to the controller, Windows 10, and so you don't see the delays that you see in some of these previous generation machines because you are communicating directly with the machine. It's swivel mounted. It does have physical buttons for future robot operations if need be. But it's very intuitive, very easy to learn and understand what's going on in that interface. A lot of good information, heads up, and yeah, very simple to use. When it comes to accuracy on this machine, here's an example of a few parts. If you go to the next slide. These are parts that were printed in Acro Extreme. It's a gray multi-purpose material, but you'll see some of the dimensions on the screen there that we're picking up. You have a little over 500 micron gaps in that middle image there. You're under 500 micron gaps on the image on the right. It just kind of gives you an idea of the fidelity and the amount of detail that you can pick up with a printer. This machine, like most of our SLA printers, runs 125 micron small spot beam and then a 762 micron large spot beam. For those of you guys that work in inches, it's a 5 thou small spot and a 30 thou large spot beam. And what that gives you advantage-wise is you can cure most of the layer using the large spot and then come back in and pick up the fine detail around the outside of each layer with the small spot, and that's how we get those nice crisp corners by being able to draw with a really small beam where we need to. This slide has a little bit on it, but if you kind of get around what we're looking at here, you're basically comparing our previous generation machine, the Pro X800, with the 750 and the 750 dual laser system. And so you can see your build time improvements just based on laser power and your number of lasers. You can see that time drops down quite a bit. So when you look at throughput, you look at that Pro X800, it was taking, much more than a day, pouring on a day and a half to build this part, where when you go to even a single laser, you're getting down close to a day. When you get to the dual, you're well within that day's time. So when you look at the throughput, number of parts that you can run through these machines, we're cutting down that build time quite a bit. And these are default styles. These haven't been optimized for that particular part. I work with customers to even get more throughput out of these machines by optimizing the build parameters for their particular geometry type of parts that they're actually printing. So there are some new accessories that go with these machines. So the transfer cart, go to the next slide, is also changed a little bit. Our previous generations of transfer carts used a lever type mechanism to move up and down. We moved to a wheel that we can turn and be a little bit more precise. If you've ever tried to offload parts in a large frame machine and your floor wasn't quite level, previous generation cart would struggle a little bit in order to come into the machine low enough to get underneath the platform, but then be able to raise high enough to actually remove the platform. So this new cart is a little more streamlined in that respect. The drip tray underneath is closer to the forks that you're going to lift the platform up with, and so it's designed quite a bit better than what we've had before. You can still utilize your Ramco agitation systems if you guys have worked with that company in the past. There is a adapter kit for a lot of their tanks. I know Ramco's changed their design a lot over the years, so you'll have to double check that, but they do have 800 size tanks that can be upgraded, but it still can utilize that same design. Offload cart can actually access that tank as well, and that allows you to basically use agitation to clean the bulk of your parts, and that's traditionally been really the best way that we've found to clean SLA parts, to take the whole platform with parts still attached, place it in a machine like this that just can move the parts up and down to a solvent, something like tripropylene glycol monomethyl ether or propylene carbonate. Some of my customers even will use IPA, depending on where you're located in the world, on how much IPA you can have in a vat like this. But that really is the best way to clean these parts up. And then the right side will either be a fresh solvent or even a water rinse if you're using a water-based cleaner. Another thing that we introduced a couple years ago with this machine, and also with a new line of materials that Richard will talk a little bit more in depth on, with the introduction of AMX materials, we've gone back to more acrylate-based formulations that, in order to get the full part properties out of those materials, it requires that we use heat and UV to post-cure those parts. And so we introduced the new post-cure 1050. It is LEDs instead of fluorescent tubes, and so you get a much more consistent curing. We have LEDs on all 6 sides, including the inside of the doors, so there isn't as much of a need to move your parts, adjust, flip. You can stick them in there. There's a nice touchscreen interface with recipes already built in. You go select your resin, and there'll be a recipe there for you. It's fully tunable. You can go in and create your own recipes if you're trying to get certain properties out of the material, or you have particular part sizes, part shapes. You can actually tune those recipes to your needs. I have customers that will even use this for other 3D printing technologies out there. It kind of becomes your one-stop UV curing box at that point. This slide really shows you the advantages that you get from more control. So we have the ability to ramp up temperatures, cure with temperature, and then allow it to cool slowly over time. And so this flight controller joystick that you see in the image here on the left, you can see light coming through, and that's because it was cured a little bit more of a stress environment. So this is AMX Rigid Black. It again, is a new acrylate-based material. The advantage of these materials is long-term stability over time. So properties-wise, unlike epoxy-based resins that we have used for many years, they stay stable. They don't continue to cure and get more brittle and stiff, like we've seen with some of the older resins. But the downside of that is acrylates do want to curl, they want to distort a lot more. So really, to get the full benefit out of these new materials, it requires a little bit more control when you cure or do that post-cure. So you can see the part on the right, we're able to hold that gap much closer. You don't see as much light coming through there. So then the last part I think I have on my list here, is 3D Sprint. So if you go to the next slide here, 3D Sprint is our preparation software. We use this same software for many of our print engines. It really is a one-stop full solution package. To give you a little bit of history, we started out with preparation softwares for many years where if it didn't help me go from an STL file to vector data that my machine can understand and build me a three-dimensional part, we probably weren't going to include it in that software. So we didn't have the ability to cut parts or shell parts or label parts or anything like that. It was very, very much a one-purpose piece of software. In the last decade or so, actually probably a little bit longer now, with the introduction of 3D Sprint, we've started adding quite a bit more tools into that preparation software. So we do quality analysis where we check for trap volumes and features that are too small to print and things like that, to being able to measure parts, making copies and scaling, obviously, being able to place parts very easily, orient parts for best surface finish supports, manually be able to orient. You can label your parts in here, and the labeling is even smart enough to hold the curve of the part, and you can embed it or extrude it. You can split and cut parts. You can go simple cuts. You can do dovetail cuts. You can add holes and pins for joining the parts later. Adding vents and drains in the quick cast build style. Support generation is huge. Editing supports is much simpler. If anybody on this call is still using 3D Manage or 3D Lightyear, it's time to step up 3D Sprint. You can purchase a version that will run even your old legacy machines, and you can see what advantages you have with a modern support algorithm that doesn't make you edit supports one region at a time. You can actually adjust support points on your part, redraw your supports automatically. It's actually really a pleasure to use compared to what we used to have to work with. Optimizations are all there. The ability to set offsets and consumptions and estimates, and being able to manage your queue so you can actually see all your printers listed in a queue and see a machine status and see where that particular machine is in your print. All that's part of 3D Sprint. And that is all for me.
Thanks, Steve. Really good overview there of the SLA 750. Just to introduce me again, I'm Rich Broad. I'm the product manager for materials here at 3D Systems. My background is largely actually on photopolymers, and I started out with SLA back in the mid-1990s. So want to try and kind of impart some of what I've learned over the years, and kind of talk to you about how we're addressing, materials for the latest generation, this latest generation of SLA machines. As Steve noted right at the start, this is the oldest technology for additive manufacturing, as we call it now, or rapid prototyping as it was then. The most developed, still gives you the most accurate, good detailed parts that that you'll get from an additive manufacturing process. And really the way that I start to talk about materials is generally about, when people are looking at additive manufacturing approaches, it's really the part in hand at the end of the process is what really counts, in terms of what it is that the whole solution is delivering. Now, of course, Steve has given you a lot of detail around the SLA 750. That is an amazing platform to deliver the kind of materials that we're aiming to make available for the system, and have available for the system right now, to push the solutions on to open it up to much more applications around production type environments. Of course, every additive manufacturing technique has its place in terms of what it's most suited for in some kind of production spaces. SLA, we know, is not the ultimate manufacturing solution in every scenario, but it fits a lot more than some others do. So I'm just going to dive in here a little bit on materials, and perhaps take a little bit of a step back, just kind of set the scene a little bit about what we're talking about here from a materials perspective on various different technologies. So if you go to the next slide, please, Elisa. So the fundamental thing I like to make clear here is about what the key difference is between what an SLA machine will do, and what we're looking at kind of moving into the space of in terms of production type materials, right? If we consider who's actually going to be specifying the kind of materials that will be an SLA machine will be producing, it's going to be design engineers, material specifiers, those kinds of people that will want to see a thermoplastic-like part, or expect a thermoplastic-like part, or expect a machine to deliver a part that behaves essentially like a thermoplastic. So a thermoplastic is a material that is a thermo-softening material, essentially. So you melt it. The most common technique is injection molding, or blow molding, or rotational molding, whatever. So you're melting a material beyond its melting point. It becomes fluid. You're injecting it or casting it into a cavity, and then it's cooling and solidifying again, or crystallizing in some way, shape, or form. And those are generally materials that are used with very well-known additive manufacturing techniques, alongside some of the traditional techniques. So those additives being SLS at relatively low temperatures, powder bed fusion, or FDM, so extrusion based machines essentially. And of course, 3D Systems has SLS and extrusion via Titan, or the medical based systems through Camovis. Next point, please. What we're talking about here is essentially thermosetting polymers. Now, these are fundamentally different, obviously, from thermoplastics. It's a very different way of achieving a solid part. You're actually reliant on a chemical reaction rather than purely a softening or a melting and a resolidification. You're actually relying on a chemical reaction to change from a liquid.
Bienvenidos al seminario web. Ha entrado como asistente en modo de solo escucha.
In this case, are used in all of those technologies that use UV as a mechanism to initiate that chemical reaction to achieve a solid part. Excuse me a minute. essentially, I mean, if we talk about innovation, generally with thermoplastics, there's a relatively low level of innovation. So essentially, the reliance there is on dry or wet blending of materials for new properties to achieve something different. With thermosets, right now we're in a period of a fairly high level of innovation, particularly around what you see with some of the the projector-based machines. And what I'm going to talk about here is how we're now adopting some of that new chemistry into the SLA, the stereolithography type environment. Next slide, please. So if you look at a timeline around SLA specifically here, what this really describes is that we're moving from basic prototyping to proper additive manufacturing. Okay, so back in the day, late 1980s, early 1990s, the range of materials for SLA particularly were very crude materials. They were very simple acrylate materials, or even some vinyl ether materials, and generally had great properties in order to be able to achieve a solid part relatively quickly in the machine. So they were accommodating some of the inadequacies of an SLA machine. So essentially, SLA machines had relatively low laser power. They drew really slowly. The materials had to be fairly reactive in order to be able to achieve a net shape, if you like, coming out of the machine relatively quickly. But that meant that generally the materials had very few engineering characteristics around them. You could achieve a bit of form and fit, very little function in terms of what those parts actually delivered. So you drop a part on the floor, even a soft floor, generally the parts would break, and you were lucky if they ended up in only 2 or 3 pieces. Normally they would sometimes shatter into lots of pieces. The real step change came with SLA around the mid to late 90s, when epoxy hybrid materials came in, and that really changed things, where toughness was significantly increased. The water and humidity sensitivity was significantly better, and allowed a certain degree of post-processing, not just UV, but heat post-processing as well, to give higher heat resistance properties, so above 100 degrees C. So you're kind of opening up more applications in that sense. And then between kind of the late 1990s and now, we kind of had a period where we've been working as hard as we can with those epoxy hybrid materials to create functionality. So you've often seen in the past materials described as an ABS mimic or a polypropylene mimic, and that was really a loose description of the general properties around maybe flex modulus or elongation at break, or sometimes kind of toughness around what kind of thermoplastic they might be like. And that was as close as it got really to a thermoplastic, because as Steve has already mentioned, those materials were very good, very accurate, and they still are. They still have their place to produce very good form, fit, to some extent functional prototypes. But they have their limitation in that generally they will work very well for a period of time, but they are very reliant on a reaction that you ultimately can't control. So as I mentioned before in the previous slide, you kick off a chemical reaction. This relies on a chemical reaction that just carries on, and it keeps on and on going, whether it's in a dark cupboard, whether it's on a windowsill, outside, whatever. And that will continue. So that cross-linking will continue, and over time it will get more and more brittle and become like one of the early materials. We are now in a position, if you click again on this slide, please, we are now in a position where we've moved to acrylate materials. We're kind of doesn't mean that the epoxy hybrid materials are going away. We're now moving into a position where we want to open up, as I mentioned, open up applications for this kind of technology to more proper production type applications for that, low rate initial production or end of life production, or even particular applications. So we're introducing and have introduced now 4 materials for SLA that are based purely on acrylate. And there's good reasons for doing that, largely because acrylates have the ability to produce significant advantages in terms of mechanical properties, adding in certain elements, which I'll talk about in a little bit, that were not possible with epoxy formulations. Epoxies generally are very sensitive to certain chemical types, which means we can't formulate additional kind of characteristics into some of the materials, like high temp, for example, or super high temperature, or flame retardancy, that kind of thing. One of the really important things, and Steve touched on this a little bit, is that acrylate chemistry, once you've actually built a part and post-cured, is way more stable. Meaning that the properties don't really change significantly over longer periods of time, which again kind of gives you a much more robust solution as we move into those production applications. Next slide, please. So this is a slide that really just describes how we categorize our materials, and we generally categorize according to a material property, whether it's designed for a specific application or as a general purpose kind of prototyping material, if you like. The testing we do to qualify and create that categorization across the industry has really historically been fairly unclear and fairly poorly designed, if I'm honest. And it kind of leaves a bit of a grey area that some suppliers have either ignored and sometimes maybe exploited a little bit. The key here is that enabling additive manufacturing parts to perform in a production environment means that we need to have a range of material that are suited to everyday applications, whether that's in automotive, aerospace, transportation, any kind of industrial or electronics type of applications. The list goes on. And often it's the requirements of an engineering part that needs specific properties like resistance to external forces, such as extremes of temperature or fluctuation, impact resistance, UV moisture resistance, those kind of things. Automotive is probably one of the most demanding, or aerospace, if you like, where temperature ranges can range from -40 to 100 plus 120 degrees C. That's relatively common in moist environments. And generally what we're trying to do is move to provide that kind of information to those design engineers, to those production specifiers or material specifiers, that really give that that kind of guarantee, or the information to enable them to make that choice, to say this is a material that's good for that low rate initial production as we move up and ramp up into full production, or for other applications towards the end of life. Next slide, please. So how do we access production applications, and how do we describe our materials? So this is really the key to how we do this. We're looking for production mechanical properties, performance properties, and testing to production testing standards, right? So our aim is to produce data sheets that have consistent data. So where in the past we were looking at data sheets that are essentially at the most 2 pages long, often only 1 page, that gave very basic mechanical properties, what we've been doing for quite some years now is building out data sheets with some consistent data across materials and across platform types, in order to really describe as best possible. Of course, that doesn't necessarily mean we're going to have all of the data available that everybody's going to want. That's not, that's not really feasible. But largely, this covers a very wide range of applications, and often we'll be testing a material according to the kind of applications that it's designed for. Important here is that we're testing to recognize standards, so ASTM, ISO standards. Excuse me. And the important thing here is that those standards, ASTM, ISO, all call for materials to be conditioned. The data, the parts need to be conditioned for the tests such as elongation and break, HDT. And if those specifications aren't followed very closely, that can really skew some things, particularly elongation and break, HDT, to have higher values. So it's important when people are looking at the data that they really understand that those testing standards are things that we really follow to the letter. So there's a lot of kind of nuances around some of this data that I really kind of want to make the point is that we are really ensuring that we're following a lot of this testing to the letter, and it's good to have the reassurance when comparing materials from a standard plastics handbook, for example, against what we're doing on the data sheets here, is that the data really is comparable. And it's the same for any other kind of additive manufacturing supplier. It's important to understand that what kind of testing they are doing, and are parts conditioned, for example, and are they following those kind of standards to the letter. There's lots of nuances around creating this data, which is very important. Next slide, please. So a key factor in a material being a production material is that long-term environmental UV, humidity, stability. So this means that the mechanical properties the day the parts are post-cured and finished should essentially remain within a small percentage over years, so not just days or months. So obviously in the past, the stigma is that all additive plastics are brittle in weeks. Yes, that was true. Right now, with the advent of the new materials that we're working with both projector-based machines and with SLA now, is that we are producing materials that have significant advantages in terms of indoor and outdoor stability tested to those recognized standards. And it's often a case where some of these properties will actually improve over time with these materials. So the material I've picked out here is Acura AMX Durable Natural. This is one of those new materials I was describing that is purely based on acrylate, so not an epoxy-based material. So what you see here is the stability of this material over time, and this is actually indoor weathering, indoor stability, showing how an accelerated aging test shows how the material really is incredibly stable and sometimes improving. But the one thing to note here is that when you're looking at any long-term stability testing, the one thing that really shows how stable a material is the elongation at break. A lot of the other properties for a lot of other materials don't change that much, but the elongation of break is one that will really suffer. And if you click again on this slide, please, you'll notice there's an example here of one of the older epoxy materials that really shows that elongation at break dropping like a stone after a very short period of time to a very low value, to the point where it's probably not usable for most applications. So a good kind of context there in terms of what it is that we're trying to achieve and what we're achieving now with these new materials. Okay, next slide, please. One of the other things we're including on data sheets now also is how these materials perform in terms of exposure to common chemicals and automotive fluids. That was a question that historically we've been asked a lot over periods of time. So this is essentially taking tensile parts and various other mechanical test parts, immersing them in fluids, and then testing them after various different lengths of exposure to show how good they are at resisting some of these chemicals. Now, I don't have a comparison here against some of the older legacy materials, but safe to say they perform nowhere near this level. They generally swell and soften within days, certainly not weeks. Next slide, please. So I'll just describe how we categorize our materials a little bit further, and this kind of gives you a flavor of how we're trying to spread. So if you just click all the way through this slide, I'll go through it. I'm just mindful a little bit of time here. So we have a range of materials for SLA that are generally categorized by flexural modulus, so it gives an indication as to the general property of material, but also materials that are then categorized according to, you know, what kind of loading they will tolerate, or whether they're designed for particular applications or not, and whether they are medical capable. And of course, the range here kind of describes a very good spread. You know, if I'd have shown you here the range of materials, you know, perhaps 10 years ago, this would be a very narrow window here. So all the way to the left here, you see AMX durable natural, which is one of the new acrylate-based materials. Anything denoted AMX is one of those new acrylate-based materials that has that additional functionality. You'll notice AMX Tough FRV0 black on here as well. The first UL94 V0 rated SLA material for large frame SLA. That would not be possible with an epoxy material. So you see here that there's a general kind of growth of this product portfolio to, again, you know, offer more of a solution from an SLA machine than ever before. Next slide, please. This is just a quick screenshot that I did of our kind of developing web-based materials finder. So on the 3D Systems website, via the link that you see down there at the bottom right of the screen, there is a material finder that allows you to search for materials based on various different categories, whether it's a material property or whether it's by particular industry, application, technology, those kind of things. So there's plenty of variables there. I've selected here for stereolithography, which gives you the range of stereolithography materials there, but then you can also then refine down. So this is basically working off the categorization that I showed you before. And is a very useful tool in order to kind of narrow down a material choice for the kind of application that you have. Next slide, please. So just to highlight a few materials here, and these are materials that have been added into the portfolio fairly recently. I got two AMX materials on here, AMX Rigid Black and AMX Durable Natural, again, both acrylate materials. Here again, you know, I'm highlighting, you know, the real difference is here in terms of what these materials achieve. You know, if you look at the AMX Rigid Black window there and look at, you know, the top right picture, these materials achieve thermoplastic-like behavior. So you notice the tensile part there is necked. So there is some yield in the material before it actually achieves a break, an elongation break. And this is actually achieving a combination that's very difficult to achieve, or has been historically very difficult to achieve in the past, is something that exhibits thermoplastic-like behavior, but still has a reasonable stiffness. Normally those materials would be very low stiffness, so, you know, only suitable for a very small range of applications. Just jumping over to AMX Durable Natural, that's another acrylate-based material. This is a super high impact elongation material with over 80% elongation at break, which is kind of previously unheard of from an SLA material. It's a super tough, super ductile material, and very suited actually to an application that we're developing a fair bit right now for removable mandrels for carbon fiber layup tooling. Acura Composite PIV is a material that it's heavily filled with ceramic to give optimum stiffness. So you notice that by the very high flex modulus there. So ultimate stiffness, The color is very much suited to PIV testing, so wind tunnel PIV testing. PIV involves shining a very high power green laser into the airflow within a wind tunnel, and the purple essentially is designed to absorb as much as that green light as possible. So a very good example of our application specific development for the SLA solution. Next slide, please. Another couple of examples here. I picked out some, again, that are very kind of good materials for us. One that is a general purpose material, if you like. Acura Extreme probably is one of our most successful, very popular materials, and this is based on epoxy. I'm not here just to fly the flag for everything new. There are some things in the portfolio, there's quite a lot of things in the portfolio that still have a very good place and perform extremely well. If you excuse the pun there. Extreme is a material that is designed and was originally designed to produce parts that kind of, if you like, were an ABS-like material. But more importantly, this was designed to have a really low cured line width and a low viscosity, which gave really excellent feature detail and really good processability, if you like. And it was grey because the intention was this was a true kind of form fit prototyping material useful for master patterns for silicon tooling, for example. And it's just a great material. It's a very easy material to run in the machine. So it's certainly one of my favorites. Cast Pro, a material designed specifically for quick cast patterns, for investment casting, to give really stable patterns with a low coefficient of thermal expansion for that shelling process within the foundry application area. Next slide, please. So I'm just going to quickly, I've noticed we have very little time, just some quick highlights here on a couple of materials that we've launched very recently, and I've mentioned these before. Acura AMX Tough FR V0 Black is the first UL94 V0 rated material for SLA. It is exactly the same material that we have available also for our Figure 4 and our coming PSLA machine. This is an amazing material, not only for its flame retardant abilities, but also for its mechanical properties. It is a tough material rather than what we would class as a rigid material, but has a really good elongation to break over 35%, which again is kind of almost unheard of for an SLA material up until this point, till we had AMX material. So I would encourage you to take a look at that. There is more data available if you go to the next slide. This was a material that was developed with using the team at the University of Dayton Research Institute alongside American Makes. They did a whole ton of work with us in kind of developing that formulation and testing the flame retardancy and resistance to aerospace fluids. And there's a whole blog on that on the 3D Systems website. So if you want to know more, I would encourage you to go and seek that out on the website. Last material here, and very briefly, because I want to leave some time for some questions. If you go to the next slide and the next one, please, is Acura AMX High Temp 300C. Now, this is the next groundbreaking material, again, based on that initial that acrylate chemistry. Is we have a material that achieves an HDT of 300 degrees C without any thermal post-curing. So up until this point, we've been reliant on advancing the cure of epoxy materials via UV and thermal post-cure. This material requires no thermal post-cure and way exceeds any kind of HDT you would get from any of the previous materials, which is shown there on the chart on the bottom left. This is a material that is ideally suited for some of the smaller frame SLA machines. It is suitable for SLA 750, but in certain scenarios, it doesn't work that well. I'd have to be honest about that, and I'd like to be honest about that. It's suitable for kind of thin wall parts with parts that don't change their cross-sectional geometry that quickly, that kind of thing. But something that needs highlighting here is, just that ability to achieve really high heat deflection temperatures is a groundbreaking thing. And that pretty much wraps it up from me, I think.
Perfect. In that case, I would like to hand over, first of all, of course, thanking you and Steve for the really insightful presentation. Before we come to the question parts, I will hand over to Paul Miller from Product Marketing, who will talk us through an exclusive offer that we are currently been promoting. And meanwhile, also please type in your questions if you have any. We would be happy to answer them. Paul?
Thanks, Elisa. Well, you just heard all about the phenomenal productivity, throughput, and quality that's possible with our SLA 750 platform. And we did reference some of the Figure 4 projector technology, particularly with some of their production-grade materials. It makes it really easy to build fast, small parts, and how they share some of the formulations. We do have an ongoing promotion that bundles both of those technologies. So you can choose either the SLA 750 in the single or dual laser configuration. This comes with all of the installation, startup, and training that goes along with it. Includes an initial vat fill, as well as a cart for easy unloading. And then we're bundling in with that a Figure 4 standalone printer, which includes its standard warranty and our extended service plan. Really together create a lot of value, and this bundle helps to deliver savings up to 25%. So I did want to just make sure everyone who joined us today was aware of that. We do need to receive orders by June 15th to qualify for this promotion, and we are looking for Q3 installations. There is a QR code on the slide here if you want to reach out to us to individualize this offer. I think with that, just with the amount of time we have left, let's just jump right into questions. Just a couple of questions came in today, but let me jump to this first one here. Steve, I think this one is directed at you. For the SLA 750, a lot of highlights went around speed and throughput of each build. Are there any trade-offs to part quality to achieve those speeds?
No, there's not. We do in production sometimes sacrifice some of that, but our goal with the 750 was to improve that throughput, but not sacrifice quality. So in the past, we would try to make a corner a little too fast, and so you don't keep the vectors in the line. That is not the case here. So you still get excellent sidewall quality, still in that optimal layer thickness range. So we're not sacrificing build speed for thicker layers or anything like that, which also is going to add additional stair stuffing and some rougher sidewalls typically. But yeah, we're still running 100 micron layers for most styles and very good sidewall quality.
Terrific, thank you. I do have a materials question here. Rich, I think you touched on this a little bit, but if maybe we can just reiterate, what was some of the inspiration for going back to using the acrylates, since it was one of the original material formulations or technologies used? Yeah,
good question. Things have moved on. Things kind of develop. The state of the art around acrylate chemistry has moved on significantly since that early period in the late 80s, early 90s, which means that we're now at the point where 3D Systems has actually been working quite a lot with acrylate-based materials, not only kind of for the projector-based technologies, but of course around MJP as well for a significant amount of time now, 15 years plus. Some of the stuff we're seeing for the AMX materials and the Figure 4 materials are the culmination of work that's happened over the last 7 or 8 years in designing new base monomers, oligomers, in order to kind of create that long-term stability and the additional functionalities of some of these materials. So it's really, in simple terms, it's state of the art has moved on in terms of those acrylates from those kind of basic building blocks that existed in the past.
All right, this one, I'll throw it out to both of you as kind of a free-for-all here. Without divulging any sensitive customer information, can you share any experiences of using SLA for production or production applications?
Well, I'll go for that straight away. There's a couple of kind of sides to that, really. There's a lot of use of additive, including SLA, as a tool or a sacrificial part in a production application, and so one of those examples that I gave with Cast Pro was using an SLA pattern as a casting pattern that is then shelled to create a shell to cast metal into, essentially. So that essentially is a true production application where customers are using have multiple installations of SLA machines in order to create casting patterns for unique geometries that wouldn't be able to be made, forged, machined, assembled in any other way, essentially. So there's that element. The direct element is a bit more kind of unique, and in some instances based around some very kind of unique industries. There are some OEMs using SLA to build parts for automotive applications, for example, or some applications. Essentially, they turn out to be applications where there are a small number of parts needed, and there are champions within those industries that are very aware of what additive is capable of, and are essentially leveraging the cost savings that they can achieve and the speed to production that they can achieve by using additive rather than traditional manufacturing techniques. And no, I'm sorry, I can't kind of share any names of those customers that are doing it.
Thank you, Rich. And then I think we just have time for one last one here. There's a question that came in. Do the lasers on the SLA 750 work individually, or do they stitch together? Steve, maybe if you can tackle that one.
Yeah, we touched on this a little bit. They work individually, so they can draw their own parts, but they also have the ability to share a part. So two different scenarios. You could have a platform full of small parts. It's going to automatically divide those parts into basically equal number of vectors, and then those lasers will tackle those individual smaller parts through the layer of that print. But you also have the other scenario where you may have one large part or a couple larger parts in your print. In that case, the software automatically divides up the vectors even within that part, and so then they share that part, and then one of those lasers will take on the duties of scanning the outside of that layer so that you do not see a seam. So there are no seams on the SLA 750.
Perfect, thank you. Well, we are out of time here. I'm going to turn it back to Elisa to help close us out for this session. Thank you.
Oh, thank you, Paul, Steve, and Rich, for putting together this presentation. Very insightful and interactive. That was really great. And most importantly, thank you to all our attendees today. It was great having you with us. And stay tuned. I can announce that we definitely will have another webinar also on Figure 4. I know we touched on some of the materials already very lightly today, so maybe that is an interesting topic for you. And I know we have Rapid coming up for our US folks on the call or in the meeting. So please join us there, visit our booth. We are happy to see you. And interested in one of those promotions that Paul mentioned, either the the single or the dual, please reach out and we'd be happy